Hey guys, so today we are going to study the topic which is called trees. So basically, till now we have seen linear kind of data structure, right? When we say linear data structure, it is the data structure like array, linked list, or stacks and queues. They all comes in the category of linear data structure because the way the access pattern is different for access pattern is linear for this kind of data structure. So there is a different category of data structure which is called trees. So basically trees, we can imagine it as a, like, let us try to think of trees first. So trees are kind of graph with no cycles. Okay, so what do we mean by this? So when we say tree is a graph, so graph kind of data structure, in graph data structure, multiple nodes can be interconnected with each other. So let's say we have this multiple nodes, right? And let's say one node here. So these nodes are connected in some fashion. Like let's say from here, here, here. So this is a graph because here, like, the access pattern is not linear. Like let's say if you want to visit this particular node, you cannot linearly visit, like in other data structure, like in array, like you start iterating from zeroth index and you keep on iterating one by one index, right? Other thing is like, so one is graph and other thing is no cycles. So what do we mean by no cycle? So let's say when I start traversing from here, let's say like a person is starting from here, a person is there with us and he is starting to traverse this tree from this node. Let's say there's a direction in this node, and he visited this particular node, and then he visited this node, child node, and then from this parent node he visited again this node. So there is no path in this particular graph where a person, when he starts from a particular node, he comes back on the same node. So that is what we mean by cycles. When we say like there are no cycle in this particular graph, we mean to say like when from starting from root node, we won't be able to reach root node again. Either we will visit the leaf node as in the node which are having no children. So if we see this is my leaf node, or either we will visit the child node. There won't be a case there won't be a case that we will arrive at the same node again, starting from that node. So that is what we mean by there is no cycles in our tree, right? So let us take few example. So what do you guys think, this whether there's a cycle in this tree or not, right? Like let's do it example with an example. Let's say we started at this node. Okay, we went to this particular child node, then we visited this particular child node of this node, and then we visited this particular node again, like we went to the child of this particular node, and then we arrived at the same node again. So we see, right? Starting from the root node, we have arrived at the same node again. So we have cycle here. And also, this is not a tree. Okay. What about let's take example of this. Do you think is this a tree or not? Right. So let's walk it through an example. So in tree, like we will be given with one node, which will be like a root node. So root node is a starting point of the tree. We will discuss like why this root node come into the picture into the tree. But for now, imagine like there is a node which is called root, and all the pointers to the child, this root node is aware of immediate child pointer. Okay, so let's walk it through. Like we started from this root node, right? We we started from the root node, and then we visited the child node 3 and 4. So this is leaf node because it is not having any children. So left or right, it is not having any children. So we see like while traversing this particular tree, particular graph, we are not visiting the root node again, right? Our path is ending here. So what we can see here is like there is no cycle here in this particular graph, and also this is a tree. Okay, let's take some example of binary tree in the real life in the real life. So in a company, like let's talk about the hierarchy in any company. When we say hierarchy in any company, we have CEO at the top, and then we have his direct reportees. Let's say we have CTO, CFO, and all other executive can be there. And under every organization, let's say like under CTO, there will be multiple organizations. There will be engineering organization, engineering system organization. There will be multiple product, as in like let's take example of Twitter. So subscription organization will be there, right? And similarly, multiple organization will be there at each level, and then employees will come, like let's say Elon. Elon is coming under the engineering organization, and Zuck. So this represent a hierarchy, like hierarchy as in like this graph represented hierarchy. So this is an example of tree. We can see that like every employee or organization can report to a particular person, to a single person. They cannot report to a multiple person. So this is an example of graph data structure, which is a tree. Okay. So in this specific session, we are going to study binary tree. Now, what are binary trees? Does put one thing here, binary trees. Let's see what are binary trees. So here in this example, we can see like every parent. So when I say parent and child, it is with respect to the direct association. When we see here, parent and child relationship is with respect to a specific part of the tree. So when we start from the root node, it is parent. It is a parent to all of the node, right? Parent to CTO and CFO. And CTO and CFO is a child of CEO. So in this hierarchy, parent and child association is there. So let us read that. So in binary tree, what will happen is every parent will have at most two children. Every parent will have at most two children. Let's take let's write it down. at most two childs. Let me give you example. So what do you think? Is this a binary tree? I will draw more examples here. Meanwhile, you all think like if it's a binary tree or not. One more example. Yeah. So let's come to this. Do you think this is a binary tree? Right. So this is a parent. This node is a parent, and it is having two child, parent and 1 and 2. So this is a binary tree. So here we have 1, 2, 3. This is not a binary tree. Here we see like this is a parent and this is one child. This is a parent and this is a one child. So this is a binary tree. Okay. So in a simple manner, like we can always think binary tree as a tree where like we will have only two children. Like there won't be any more than two children. There can be no children as well. If we see in this particular example, there are no children to this particular node. And this property has to be consistent with all the nodes. Consistent with all nodes. It won't be the case that few of the nodes are following this property and few of the nodes are not consistent with this. In that case, it won't be a binary. Okay. So at most two nodes. So this is our definition of binary tree. Okay. So now let's take example of how do we represent a binary tree. Okay. Representation. We will talk about representation of binary tree. So till now we have discussed every binary tree will have one parent, one child, at most two child. Okay. So this can be association, one association. This can be binary tree. This can be one more binary tree. Okay. So what do we need to start on a binary tree? So if we see this particular representation, given a reference to a particular root, a particular node, which is at the center, which is at the start of our tree, right? We can reach to any node of our tree. Let's say like if I have a reference to this particular node, I will be able to, and this node is having references to the child node. So this is having reference to this node, and this is having reference to this node, and again this. So starting from this particular node, I can visit any node which is present in this tree data structure. So, um, so like to represent this tree, we will need a node which is at the center of our tree, which is called the root node by convention. Okay. So we will say like we will need one root node. Now let's think like how we are going to represent a particular node. What data a particular node should have. Okay. Every node will have certain kind of values, right? So in this previous example, we can see like designation. So every node has certain set of values like designation or all and all. So one thing is like in every node, anatomy, if we talk about anatomy of a node, we will need a value in that object. Value will be the value which is the value of that particular node. Okay. And then if we see this example which we have drawn earlier, we will need pointers to the left and right child node. Right? When I say left, left is with respect to the node which is in the discussion. So this is the left child node and this is the right child node. So in every node, we will need a reference to left child node as well as right child node. Okay. So using this three information, let's think like, do we need any other information to visit every node of the tree and also extract value of every node of the tree, right? So let's say like we once we have the value, we visited any node, we will have that object will have this value of that particular node, and then we can analyze it in the manner which we want to solve a particular scenario. Okay. And starting from any node, when we can say like, hey, what's your left node, what's your right node, we will be visiting left and right, and from those nodes we can again visit left and right nodes in that manner, and that way like we can visit the entire tree. So this three value is sufficient to represent one particular node of a tree. Okay. So minimum info. So this is our minimum info to traverse the minimum info at node level. Also, to traverse the tree, what is the minimum info? As we discussed, we just need a reference to the root node to traverse the entire tree. Traverse the tree, minimum info is root node. All right. Now let's see like how we will represent it as a it in a program. So let's think of it. Let's say we have a particular class. We will create a class of this particular class. We call it node. Better, let's call it tree node. Tree node, and then we will say we will define the constructor of this class. Define init node. Here we will pass the um, optional value. Value. This is optional. We will mark it as none. We will mark it as optional for now, and we'll say this particular class will have to will self dot val equal to value and self dot left equal to self dot right equal to none. So what we have done here is like in a tree node, we are allowing the caller to initialize a tree node with the value, which is an optional parameter. And when this node is getting initialized, we are marking the left child and the right child as none. Okay. So let's see like how this particular node will be initiated. So let's say we want to create a particular node. So initially, when this node is constructed, this will have a value which can have optional, which will be none, or which will have certain value. Okay. And initially, the left child will point to none, and it will point to none. And when we want to have a reference of this node to certain left or right child, we will say like node dot left is equal to right node, not right node. It will be it will be okay. So in this way, we can construct the whole tree given certain values. All right. Mm. Now we will do one example of this. So let's revise quickly what we have done till now. So we started with tree, like we started with the question like why we need tree data structure. We already have linear data structure which solves our problem, which solves multiple type of problems, right? But the thing we observed here is like the linear data structure, the access pattern is only linear. It is linear data structure because access pattern is linear. We can only go in a linear fashion. And when we see a problem like this, like the hierarchy which is present in any organization, this linear access pattern or linear representation won't work for this kind of data, this kind of real life problem. So for that, we thought it is we need a graph kind of data structure, and this graph kind of data structure which is having no cycles, no cycle as in when we start from a particular node, we won't be able to be while accessing the child node, we won't be wasting this node again from any child node, right? So that is what we meant by like having no cycle. And then we discussed was what is binary tree. So binary tree, at most two child. Any node can have at most two child, and all node has to be consistent with this property. Then only it's a binary tree. Otherwise, it's not a binary tree for us. And then finally, we discussed about the representation. We discussed what things this node object should have. Node object should have the value of that particular node, whichever is stored in that. For example, uh, Elon Musk, that particular node, employee node or CEO node, or Parag Agarwal as CTO, right? And then left and right. Left and right is the child's left child or right child pointer. And then we concluded that given if we are just given the root node, we are good to visit any other node of a tree. When we start from a root node, we can visit any node of the tree. We can visit the left node and then the child of that left node. In that way, like this pattern, we can visit any node of the tree. Just keep this in mind. Like we will see like how easily we can visit every node of the tree in next few minutes. And then we represented a tree node, like we initialize the value and then we initialize the left and right as none initially, and we saw like how we can reinitialize the left child and the right child. So let's do a question for this. So we'll solve a question. So the question is, given a binary tree, given a binary tree with n nodes, with n nodes, number of edges. Number of edges we have to find of this binary tree. Okay. So let's think of this question in a very at a very high level. So in this question, it is not specified what could be the structure of the tree, right? Given n nodes, the um, tree can be of this manner, only one child node, or tree can be of this manner, where every parent has two child or none, right? We are not given the structure of the tree. We are just given there's a binary tree with n nodes, and we need to find the number of edges in that tree. So let's try to make an observation here. So here, if we see in this tree, let's see the property of each node. Okay, let's pick up this particular node. So what we can say about the parent-child relationship, when we are talking about the edges, we have to talk about this particular connections between the node. So what we can observe about this relationship, right? So here, let's say like can have parent can have 0 to 2 childs. Okay, either it can be 0, 1, 0 to 2. All right. Now let's talk about the um, when this is a parent, it can have 0 to 2 child, right? Now let's think when it's a child, how many node can it have? When child node, let's draw observation from here. Child node can have 0 to 2 childs, or it can have only one parent here. Now these are all the possibilities of the relationship between our trees. Now we need to figure out like which relationship will be easy for us to find the number of edges. So let's say like here we say like 0 to 2 nodes, 0 to 2 childs are there for every parent. So it is like 0, 1 and 2 category. We need to count for all these three categories. So it is useful, but let's keep it aside. And then when we say like one parent, every node definitely is going to have one parent except the root node. So one exception will be there, except root node. Every node is going to have one parent, right? So there are n nodes. So how many n nodes? We have n nodes, right? So how many parents we will have? N parents. N parents, and that will be -1 for root node. So see, like this small observation, like we have broken down the problem into few stages. First, what we identified, if 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 any kind of ordering matters for us, if any kind of ordering is specified in the question, and then we concluded there's no ordering specific information in our question, and then we tried to draw observation from by looking at a particular node. We have drawn observation that parent can have 0 to 2 child or child node. Then we analyzed the node as a child node. Then we concluded it can have further 0 to 2 child, or either it can have one parent only, one parent association. And that is except the root node. So root node won't have any parent, right? So from there we concluded that the total number of nodes in a tree with n nodes is n minus 1. Total number of edges, my bad. Number of edges.